All right. This is lecture 10 in the Arithmetic Harmonic Analysis series. We'll continue with Euclidean maximal functions. These we've already seen a few of, right? The Hardy-Littlewood maximal function and the spherical maximal function, which I'll recall in a minute. And the main point of today, or this lecture and the next, is to prove Stein's theorem, which I'll recall momentarily. But just to remind you of the prototypical maximal function. Again, that's the Hardy-Littlewood maximal function defined by averaging over balls at each point and then taking the biggest average. And the main theorem about this was that it's a very good operator. It satisfies LP to LP bounds for all p bigger than 1, and it satisfies this surrogate L1 bound known as the weak type 1,1 bound. In contrast, Stein's spherical maximal function is defined by averages over spheres, the shell of a ball. And so you have to be a little more careful. We were going to deal with a priori estimates, meaning we're going to assume that all of our functions are sufficiently nice in some way. And you define the spherical maximum again by just the biggest average at each possible point. This operator isn't bounded on LP for all p bigger than 1 anymore. It's bounded depending on a range. Its range of boundedness depends on the dimension now. And it's a range that is always, that strictly excludes 1. It doesn't have a surrogate at or near 1. But for us, it's always going to be in a range that contains L2 and L infinity. Right? What we'll actually prove is Bourgain's restricted weak type inequality for the spherical maximal function, which is a weak type d over d minus 1 to d over d minus 1 inequality, where d was the dimension. And it's just that's just the bound written here below. Okay, we pick some altitude alpha. This is for all alpha greater than 0. You have a bound on the level sets of the maximal function. When you apply it to the characteristic of some function, or sorry, of some measurable subset f inside Euclidean space. Okay, and this also only holds for d greater than or equal to 3. This it's not weak type. Yeah, well, okay, it's restricted weak type. The restricted just means it's these functions, these characteristic functions of sets. The weak type bounds here, so the condition without restricted actually fails. Stein showed that in his original paper. And this also isn't true when d equals 2. So it's not true for the circular maximal function in the plane. You don't have the weak type nor the restricted weak type bounds, which would be L2 to L2 here. The construction for that actually uses some interesting Bezukovich sets, some exotic collections of circles in the plane. I won't go into that proof. That was done by Seeger, Tao, and Wright. I want to say late 90s, early 2000s, thereabouts. Before diving in, were there any questions about the stuff from before or what we're trying to do? For instance, any questions about this restricted weak type inequality? All right, I've mentioned these things a couple of times. You'll have plenty of opportunities to ask questions as we go along. I also want to recall a little bit of notation and setup that we have. We're only considering isotropic dilations, right? I take a single sphere, the unit sphere, and I consider an isotropic dilation of it to define all my other spheres, meaning in each direction, I am expanding by the same amount, or I'm contracting by the same amount if I take a small t here for my contraction. And the way we're going to define operators in the future, because we're going to look at low and high frequency pieces of the spherical averages, it's going to be by the same sort of, it's by the same isotropic dilation formula that we discussed previously, right? And that was just, I start with my my function, I scale out by r, so it looks at it like at a unit scale. I apply my averaging operator at that scale, and then I zoom back in to the original scale. And that's how I define my rth average once I've picked a fixed God-given first average. Okay. And this works well with measures. Okay. In particular, if d mu of r is the measure corresponding to a of r, then we know that mu r, the Fourier transform of mu r at a point c is the Fourier transform of mu, or mu1 if you prefer, at r times c. And so c is a vector, right? So when I say r times c, I just mean each coordinate is multiplied by r. And this is that isotropic scaling. Each coordinate is dilated by the same amount. Brilliant. So the main point of the last lecture was to prove this first inequality. We showed that if you take the surface measure on the unit sphere, and where a surface measure in this case meant either the delta measure, Dirac delta measure, or the induced Lebesgue measure, and you look at its Fourier transform, then it has certain decay bounds at infinity. So when c is large, it decays like c to the minus d minus 1 over 2. And then when c is 0, you're just picking up the mass of the spherical measure, which we normalize to be 1. And so that's the only bound you get at c equals 1, x equals or near 0. Right? But again, the main point of this estimate here, the difficult part, was what was happening when c was going to infinity in any direction. Now, we have a secondary bound, which I did not prove, but it's similar enough to that bound that I'm going to leave it to the reader and just hope you take it for granted, at least in the analysis that we do today. So that bound is just if you look at the gradient of the Fourier transform of the surface measure on the sphere. And it's basically you get the same bound as before, except you have this new factor of the absolute value of c appearing. And that means when c is pretty large, as it's going to infinity, this bound is actually weaker than the first bound. But still, that's going to be fine for our purposes. And it's an inherent part of the study, especially when you're looking at maximal functions over averages of hypersurfaces. And this, the fact that this derivative, this gradient will come into play, and when it does, you lose this factor of c, is what I'll mean by losing a derivative, right? You might ask, well, can you do better? Is that c really necessary? And it turns out it actually is. When you give the asymptotics for the Fourier transform of the surface measure, then this genuinely appears there. So that's the best you can hope for. But we don't need any asymptotics. We just need these decay bounds of the right order to prove Stein's theorem and Bourgain's theorem. Right. So the main tool that is used in setting these Maximal functions in general. Okay, so the key geometric input, let me back up for a moment. The key geometric input was relating the curvature of the sphere to the decay estimates for the Fourier transform. But the key tool that allows us to use that is Littlewood Paley theory. So Littlewood Paley theory is the following, which I'll go into a little depth. I won't go into this is something from about the 1920s or 30s, I think 30s, and it's been developed for many decades since, but I'm just going to give a very slim introduction to the parts that we need. So what do? We pick our function phi. That'll be some Schwartz function radial, such that it's 1 on the unit ball inside of RD, and it's supported inside the ball of radius 2. It's centered at the origin in RD. So as a profile of it, if we look at just the radius of our, we have this familiar looking function. So at 2 and minus 2, so this is r actually. There's no negative real number, but you know what I mean, sort of making it symmetric looking. It's 0 outside of this. And then at 1, it's 1 up until in that symmetric range. And then in between it's C infinity, and it attenuates to 0 as you get towards 2. Let's assume it's monotonically decreasing. I didn't say that before, but I also want monotonically decreasing. So what is this thing? Basically, what I would really like to do is I'd like to just take the characteristic function of the unit ball here. But that has a sharp cutoff, and that causes technical complications. This smooth cutoff, this multiplication of that function, of the characteristic function of the unit ball, makes life so much simpler in terms of doing the analysis. And taking shorts allows you to do lots of things, right? Because this is harmonic analysis, we'll often do the Fourier transform. And when you have a Schwartz function, the Fourier transform is also Schwartz, so it has all the decay and regularity that you could want, or at least hope to get away with. Great. Right, so once I fix this nice function phi, I can define my Littlewood Paley operators. So there's one for each, that should be a boldface Z. There's one for each integer, right? So if I take a j that's an integer, I have an operator, a Littlewood Paley projection operator, pj, and it's defined by taking the Fourier transform. So it's defined as a Fourier multiplier, right? In particular, I'm going to use to actually define pj on the physical side, we're writing it as the inverse Fourier transform of the Fourier transform. All right. So when I define the Fourier transform, this is uniquely defined as long as that input is an L2 or Schwartz itself. And we're going to actually use a Schwartz thing, so we'll get an honest function back. Right. So how do I define that? I am just going to define it as multiplying by this difference. Okay. So what does that do? If my original function phi supported in the ball of radius 2, so phi of c over 2 to the j is supported in a ball of radius 2 to the j plus 1. And it's 1 on the ball of radius 2 to the j. Again, all the balls I'm talking about now are centered at the origin inside of Euclidean space. Great. Now phi of c over 2 to the j minus 1 has the same properties, but it's supported in a ball of radius 2 to the j minus 1 plus 1. That's just 2 to the j. And it's 1 on a ball of radius 2 to the j minus 1. So their difference is 0 inside the ball of radius 2 to the j minus 1. And it's 0 outside the ball of radius 2 to the j plus 1. And that means its profile looks something like, and this is taking some very artistic liberties here. So I'm 0 for a while, oops. And I shoot up for a little bit and come back down. Right, and this is like 2 to the j minus 1. That's 2 to the j plus 1. And I actually hit 1 very briefly at 2 to the j. Okay, so that's what I multiply the Fourier transform of my function by. And that Fourier transform, I then invert, right, to define my Littlewood Paley piece. So that's pj. There's a simpler definition for p for another projection. And that's where I look at all the frequencies that are less than or equal to 2 to the j. And that's just by, I don't do that telescoping sum there, the difference of one term and its predecessor. Instead, I just multiply the Fourier transform by phi of c over 2 to the j. And again, if phi were actually the characteristic function of the unit ball, then this would say, I take my function and I cut out all the frequencies that are bigger than 2 to the j. And now what we've actually done is we've cut out all the frequencies that are bigger than 2 to the j plus 1. And we've kept as pure as possible all the ones of up to 2 to the j. And then we smoothly interpolated in between, weighting the frequencies between 2 to the j and 2 to the j plus 1, so that we get this nice smooth transition. Okay. So those are the operators. Let's see what these things actually mean. Well, I've written p less than or equal to j because in a certain sense, it's actually a sum over all the Littlewood Paley pieces up to j. So this is all integers k. Oh, sorry, that should be a k. Silly me. And now what do each of these things mean? Or recall, each of them is frequency localized, meaning its Fourier transform is supported in the ball of radius 2 to the j plus 1. And psi j is going to be this right here. For future reference, I will write this as psi j of c. And I will write this as phi j of c. Okay. So pj and p less than or equal to j are operators that take your function and localize it in Fourier space up to in a ball of radius 2 to the j plus 1. And that means that you can think of your new function pj of f or p less than or equal to j of f as a function which is essentially constant on balls of radius inverse the scale, which is 2 to the minus j. Okay, so if j is very large, I'm picking up big frequencies. Big frequencies oscillate a lot, very rapidly, which means I'm only locally constant at a very small scale, right? Because otherwise I'm oscillating too quickly. And so after a sufficient amount of time, I'm going to have moved significantly. Alternately though, if j is quite small, -10 to the 10, yeah, that's a small number, then, my function is actually very regular. It's varying very slowly and smoothly, and it looks basically the same in a very big window. Okay, so why are these called projection operators? They aren't honest projections, but they have a lot of properties that are going to be useful for us. The first is Calderon's self-reproducing formula, which tells us that if I compose two operators, then the smaller one wins, the smaller one being measured by the index j as an integer, ordered in the usual way. All right, and that just follows because if I look at the Fourier transforms, this just turns into honest multiplication, and that is the multiplication of these functions right here. Now, since this buddy was 1 on 2 to the j plus 1, in the ball of psi radius 2 to the j plus 1, and this buddy is supported in the ball of radius 2 to the j plus 1, multiplying 1 by this doesn't change it at all. It just stays the same. So that's how we derive this identity. And you can see more generally, like I said, the smaller one always wins. And the keen observer might say, well, what if you do it the other way around? What if I say, I look at P, J, and PJ plus 1. So firstly, remember that we are talking about operators as being composed from right to left. And so if if I apply F here, then it's first PJ plus 1, then PJ. Okay. Well, this actually equals, less than or equal to. This actually equals both of these. Because it's multiplication on the Fourier side, it is just, you can swap the order, right? Multiplication over here, it doesn't matter if I turn this back or forth, right? If I write it the other way around. So that's fine. And that's what I mean. That's why you can always pick the smaller index. That's what you get, right? Now, what if you choose the same index? Okay, well, you don't actually get that as a projection. If I was a projection, I would want P composed with P, for say projection P. Well, that would just spit out the projection again, right? It doesn't change once you're already restricted. That's not the case for any of these operators. And that's because simply phi times phi is, I haven't assumed that it equals phi to start. So if phi was equal to the characteristic function of the unit ball, that would be true, right? Then phi dot phi is actually equal to phi. But because we've done the smoothed out process, it's actually never true that they're going to be equal. So it's never the same projection, right? Great. But for all intents and purposes, it's pretty harmless for us. You get something that is almost as good. And in itself, I could just think of I could have started instead of with phi as my defining multiplier. I could have started instead with phi squared. And that wouldn't have harmed anything. That could have been my other system of Littlewood Paley multipliers of projections. So you should think about it as roughly being the same, morally being the same, but not quite the same. And that causes a few very minor technical wrinkles. Right. One final thing is in terms of also orthogonality, we have the following relation. So I said that these aren't projections, right? If they're also projections, then you would expect that any two of them would be projecting onto a different space. And therefore, two distinct ones would project onto two distinct spaces and be zero if you could do them, if you combine the two. That is not quite the case. If I pick two j, so I have one j that goes like that. And then I have another j that comes and goes like this. And then there could be a third one, right? So this blue one and this black one don't interact at all. And they would be independent, acting orthogonally to each other. So those two, when you combine them, when you apply P of that one, P of blue and P of black to against each other, that would give you the zero operator. However, there is some interaction between red and black here, and that will give you something. So that won't give you the zero operator. That's just measured in terms of how far or close these indices are apart, as you can see. And if you think about it for a moment and write things down, basically, the only ones that interact with each other are the neighbors, right? If I fix my j, I look at pj, then the only one that interacts with it is pj plus 1 and pj minus 1. In other words, if I take any pk, where k minus j is bigger than 1, and distance from each other, or p and j are, sorry, k and j have distance greater than 1 from each other, then these things are orthogonal. Okay, we'll make use of all these properties shortly. So are there any questions at the moment? Have I made a typo and defined things improperly? Great. Okay, assuming everything is fine. Let's start with the Schwartz function f and talk about a few of these basic properties for the Littlewood Paley projections. The first is the series representation. I said there was this imprecise sense where the p less than or equal to j is a sum of all the pk for k less than j. Well, let's make that a bit precise. The first is that the sum of the pj's over all the possible j's is basically the identity operator. And that works at least when you're Schwartz, and it also works in L2 sense. And the way we can mean that is that if I look at p less than or equal to j, well, as j tends to negative infinity, this operator tends to 0. And as j tends to positive infinity, this operator tends to the original function. Okay. That's one nice property. Another property is this orthogonality that I was talking about. I just mentioned that, if you're sufficiently far from one projection, then you're going to be orthogonal to it. Similarly, you know that each projection is self-adjoint. Okay. And it turns out the really interesting thing actually is that you can compare the L2 norm of the original function with a little L2 norm of the L2 norms of the Littlewood Paley pieces of your function. And we'll prove that in a minute. There are two more properties to get through real quick. The first one is the cheap Littlewood Paley inequality, which tells us that if I look at all the low frequencies of a function and measure that in the LP norm, it's bounded by the LP norm of the original function up to some constant. And this is true for all finite LP norms. And it's also bounded by the sum of the LP norms of the Littlewood Paley projections. Okay, this is a cheap one because you do very little work to prove it. Essentially, you write out what this Fourier multiplier is a convolution operator, and you apply Young's inequality to prove this bound. And then for this one, you just write, you use that series representation, and you just apply the triangle inequality in terms of norms. Nothing deep there. However, this fourth point is actually why it's called a theory, and that's the Littlewood Paley square function, which is defined by looking at each Littlewood, so at each point x, you get each pj f of x, you take absolute value, square it, and then square root over all the j's, or the sum over all the j's, and that gives you a square function. This is a function defined on RD as well. And the very cool thing is that the LP norm of your square function is basically the same as the LP norm of your original function. This is telling you there's these operators are really acting independently, right? If you think about this from like the central limit theorem point of view or random variables, this is telling you that each of these PJs is really acting independently of the others. We won't go into the proof of this last thing. That would take a whole lecture itself, I'm sure, to go into all the singular integral stuff that you need to do and prove it. But it's in a lot of, it's in any introductory text in Euclidean harmonic analysis, and you can find it there. For instance, in Stein's books or Tao's notes, so on. Let's prove the first few properties real quick. I want to show that my function, so I was saying pj of f, so p less than or equal to j of f. J, it tends to 0 as j tends to infinity, minus infinity. And then it tends to f as j tends to positive infinity. Okay. Yeah, so let's do the top one first. The key observation is that these phi functions, when I have them scaling them by 2 to the j, well, it's just contracting the support as j goes to minus infinity until it's basically just 1 at the origin and 0 everywhere else. That function is almost everywhere 0. So on L2, it is basically a 0 function, and you're just multiplying 0 times f, and that gives you 0. Okay, it's not a Dirac delta function. It's going to an honest 0 function. Well, then that means, so that gives you the L2 sense, and you can also get it pointwise if you start with a Schwartz function f, because if your function is 0 L2 norm, that means the function is 0 almost everywhere. And since you're Schwartz, that means you're actually 0 everywhere. Great. Sorry, not conversely, in the other direction, if I'm taking j to infinity, this tends to f because these functions now are getting dilated. And so I'm becoming 1 and 1 on a longer and longer stretch until basically in the limit, I'm just 1 everywhere. And that's multiplying the Fourier transform by 1 everywhere, which is not changing it at all. Therefore, I have the same L2 norm as my original function. Because I just became the original function, at least the Fourier transform did. And if you're a Schwartz function and you, right, so if you have two functions that have the same Fourier transform, then those two functions are equal when you're Schwartz. All right, let's get to the more interesting L2 property. So the Littlewood Paley projections are self-adjoint is easy to see if you look on the frequency side. And that just boils down to the fact that I assume phi is real valued. So you can flip the function over on in the inner product, right? You have PJF, PJF, and then the inner product on L2 of RD and Plancherel or Parseval, whichever one it is, means that the Fourier transforms are equal. And then you write out these in terms of their multipliers, and you just can move one over. Then we already saw the orthogonality relation. And so what's really left to show is that the L2 norms are comparable, which I didn't mention. That's a weak form of the Littlewood Paley inequality, LP4, because you can switch little L2 norm with the big L2 norms here. But all right, how do we do this? We just use our series representation. F equals the sum of PJ of F. Great. And then you expand the sum. This orthogonality says what seems to be a two-dimensional array of inner products of PJF and PK of F is actually essentially a one-dimensional array. It's the diagonal where J is equal to K plus the next two lines off of it, right? When J minus K is 1 and J minus K is minus 1. So you're just adjacent to the diagonal. And you just apply Cauchy-Schwarz, sort of in the usual way to do this. There's, for each point, each J say, I only have two neighbors and itself to worry about. So that's three things. And when you apply Cauchy-Schwarz, you just lose a factor of 3. So that when you take the L2 norm without the square, you just pick up a square root of 3. Cool, nothing hard there. But the lower bound you have to worry about as well. And so you just, again, you start off in the same spot. And now the way you prove the lower bound is you just show that all the off-diagonal terms are contributing positively, or at least non-negatively. And that boils down to the same thing like the self-adjoint property, which I've written out here now. Great. And then I'm just going to leave, I've already mentioned the third point and how to prove it. I'll leave the details of that as a exercise for the reader. So are there any questions at the moment? I don't expect everyone has seen Littlewood Paley theory, and we don't need the full force of it. We'll develop everything we need shortly. Okay, so I've thrown a bit of definitions and some very elementary properties at you. Let's start getting to how we can use these things. So here is the one step that always surprises me in this study. It really tells you that this Littlewood Paley theory is very useful, especially for analysis on L2. Okay. That was perhaps bad notation there. Let's assume we have some convolution operator. So what's a convolution operator? That means that if I plug in some function f that I'm applying my convolution operator to, which I call t, then it's actually just convolution with some measure, which I'll call mu. And that measure mu, we're going to assume is nice enough properties for all the arguments below. If we don't need a lot of niceness for the spherical maximal function, we only need like, I don't know, d over 2 derivatives or something like this. You can just assume if you want that mu is Schwarz, and that'll be good enough with sort of standard approximation arguments to bootstrap you anywhere else we need to go. But what kind of operator am I going to look at? I'm going to assume that this convolution operator has frequency support in a particular annulus. And that annulus for us is, so what do I mean by frequency support? I mean that when I look at the Fourier transform of mu, it's supported in this annulus. Right here. Okay, and now I'm going to define a whole family of operators, these T of R. They're defined by those isotropic dilations. If you remember correctly, it was, so T of R will be dilate by R equals a T dilate by R inverse. And those are ones. And what our lemma says is that if you just look at the dyadic maximal function for this frequency localized operator, and you assume that it's bounded, then you actually get the full maximal function, where I'm not taking a sup over only R between 1 and 2, but a sup over all the positive reals, and making full use of these dilations. Then it turns out it's also bounded in L2. And I've only lost a factor of 3 compared to the original operator bound. That is a bit to unpack. But basically what I've said is that if I only look at a relatively few number of the possible averages to form a maximal function, then when I take the full maximal function, I throw in every possible average, I can use boundedness of one to imply boundedness of the other. I should say clearly, if this one is bounded, that implies this one is bounded because it's just a smaller range of supremum. So the real interesting thing, of course, is the fact that we can go from this dyadic one to the full one. All right. All right, all right. For the moment, a lot of the argument actually works for any LP space, and so I'll just keep it general, working with an arbitrary P between 1 and infinity, and then when I actually need to go to L2, that's when I will. Okay. So what's the first thing you might want to try? If you're just going to be a bit rough and just bluntly doing things without thinking too much about it, the first thing you might want to try is breaking up the supremum over all possible radii into dyadic scales. Right? So in particular, the sup over R positive is equal to a sup over J and Z, and a sup over right, 2 to the J less than or equal to R less than 2 to the J plus 1. Okay. I take a sup over each dyadic range and then a supremum over all the possible ranges. And I don't really know how to take a sup over, I don't know how to efficiently do that. So I'm just going to say, I'll take the worst, I'll take all the dyadic ranges and just sum them up. It seems like a foolish thing to do. And indeed, it usually is. But that's how you get this inequality. And then when I say this here, I just mean that this is true. So you just get this sort of bound for the moment. And you think about it, and you actually use your dilations, and you show that, if I pick any positive big R, and I look at all the radii between R and twice R, well, this, by a rescaling argument, has the same norm, the exact same norm, as if I had just chosen that big R to be 1. And so I looked at the radii between 1 and 2. And so then it seems like this is incredibly foolish, because I would be just adding up, I'd be adding up this number infinitely many times. But this is where Littlewood Paley is important. And this is where we use the frequency localization of our operator. What you realize is that, okay, so T, which is equal to T1, was frequency localized to 2 to the K less than or equal to C less than 2 to the K plus 1. Well, if I look at TR, then it's frequency localized in an analogous range. All right. It's not the same one as T. It's scaled with R. And that's going to allow us to use Littlewood Paley theory. The operator t, which is frequency localized, actually induces a frequency localization on your function. And you get to use that. This is where the sort of pseudo projection property of the operators is coming into play. All right, so how do we do this? Well, remember that PJ are Littlewood Paley projections. Let's introduce QJ. I said that PJ, or at least I said less than or equal to PJ and less than or equal to PJ less than or equal to J. This right here, I said is roughly itself. And this is, now we're gonna get into what roughly is and use that to our advantage. And I'm gonna do that by introducing these QJs. And what is QJ? It's I take PJ and then I take PJ plus 1 and PJ plus 2. All right. This function has frequency support in the annulus 2 to the j minus 1 up to 2 to the j plus 3 because of the localization of the PJs. Right. These are localized. Each PJ was localized to 2 to the j minus 1 up to 2 to the j plus 1. So when I add the next 2, I move up 2 scales. Right. Additionally, it is identically 1 inside this bigger annulus, 2 to the j up to 2 to the j plus 2. Right. That has the following property. If I take T of R, where R is between 2 to the j and 2 to the j plus 1, then TR composed with QJ plus K is equal to TR. And again, these are things that you can, on the Fourier side is multiplication. So you can actually change the order and you get this inequality, this equality for free as well. So here we're really using the fact that, let's draw a picture. I said that in 2 to the k, 2 to the k plus 1, I said my frequency multiplier is doing whatever it is doing here. All right, but it's supported in there. And then I say, all right, I'm going to take a function that is 1 on here and doing whatever else outside of it. But when I multiply these two together, of course, I just return the black one, the multiplier, because it's 1 everywhere inside, everywhere it's non-zero or possibly non-zero. So it doesn't change it at all. Sweet. So we still use our sequence of radii being broken into these dyadic scales. Let's pick a scale, 2 to the v, and consider the dyadic maximal function for that one. Well, for free, I got to throw in this frequency localization, this Littlewood Paley operator. So applying our hypothesis, which remember said that's the soup. So it said right here, if I took 1 less than or equal to r less than or equal to or less than 2, then I got that this was less than or equal to c times, this is where I'm using 2, but you could have a more general hypothesis. This would be less than or equal to c times f and LP to the p. That's c to the p then. But I got to throw in this extra localization. Okay. That's useful, or it will be momentarily. And so at this moment, you'd really just like to say, okay, I can add up all these LP norms and I can just bound that by the original function. And by doing so, by something like this, say, I replace the QJs with some honest PJs at the loss of maybe some constant, and you think, okay, then this is just, right, the sum over PJs of F is just F, so I got the LP norm of F there. But that last inequality isn't always true. And this is where we're going to specialize to taking P equals 2 now. Then you just use Cauchy-Schwarz, but a very elementary version of Cauchy-Schwarz. If I take 3 numbers, say they're non-negative, I add them up and square them, that's less than or equal to 3 times the sum of their squares. So I can bound the square, the absolute value of QJ squared, by 3 times the sum of the pj squared plus pj plus 1 squared plus pj plus 2 squared. And what does that give me? Well, that gives me that when I look at this sum, I get that it's bounded by 9 times the L2, the little L2 norm of the L2 norms of the Littlewood Paley pieces, right? Which we already knew from the theorem before that this is at most the L2 norm of f squared. The sum is, so then I lose I have lost that factor of 9. And that's why the constant goes from C to 3C. Now you could do this for P greater than or equal to 2 by making use of the Littlewood Paley inequality, this LP4 that I mentioned but didn't prove. All I'm using is the version of LP4 when P is equal to 2. And that again is just LP2 property from earlier. So any questions about that lemma? Okay, just take a moment to catch my breath. Let's go on a little bit further before we move to the next lecture. So for this, I need a little bit more notation. I'm going to introduce these dilation operators that are LP normalized. They just help me keep track of when this is true, when the LP norm of a function is equal to a certain dilate. Okay. It's nothing, this is just some notation, nothing fancy going on here. It does have a nice property that it intertwines with the Fourier transform in a certain way. And that is, so if math cal F is the Fourier transform, then if I dilate and then do the Fourier transform, that's the same as doing the Fourier transform first and doing a different dilation. These are all just changes of variables that you see in doing the integrals. And the dilation inverts the t, that's changing your scale. But it also changes the exponent, p prime. It changes it to the dual one, which is defined by this linear relation, or inverse linear relation. Again, these are all immediately verified by just doing changes of variables for the Fourier transforms and these operators. Now, the one that we're going to use most is that how L infinity dilations and L1 dilations interact with the Fourier transform. Okay, we've already actually used this quite a bit in talking about the different ways to define, T of R, where R is positive, starting with a single operator and then defining all of its isotropic dilations. This is just going to be, I have 2 competing ways to dilate, because I'll dilate on the frequency side on the one hand, and I'll dilate in the spatial side on the other hand. And this relation keeps track of that. Okay, there's another thing we need to do. So with that L2 lemma in view, I'm going to introduce, I'm going to break up the spherical averages into a low frequency piece and a high frequency piece. And I'm not going to specify what high or low is at the moment, but and it won't really be too well reflected in the notation, but it's going to be fine for us. So what am I going to do? I'm going to take my spherical average, I'm averaging over the sphere of radius 1, and then I say P, the low frequency projection, or my operator S low, is just going to be, I take F, I apply the Littlewood Paley projection to all frequencies up to scale 2 to the j, and then I apply the average, this average over the sphere of radius 1 at every point. And the complement of that is going to be this S high, the high part of the spherical average, where I do the opposite operator. I have P greater than J being applied at first. And then we use our isotropic dilations to define SR low and SR high. Okay, and then there's just one more piece. SJ will be A1 composed with PJ. And SJR is, of course, the same isotropic dilation as we've been using this whole time. Okay, that's a bit of notation. What it's really trying to get at is saying that I can take my averages and I can break them into two pieces, a low frequency part and a high frequency part. And our analysis splits into this dichotomy. We'll prove two bounds, one for each of those parts. And then we're going to optimize them together later. So let's prove this L2 Sobolev inequality and end there for next time. Great. So what's our Sobolev inequality? If I take some, say, C2 function, but if you want, just make it smooth. It's going to be smooth on an interval I, a real interval, some subset of the real numbers, open subset of the real numbers. And if I take a parameter L, that's at most the length of the interval. Then when I look at the sup of my function inside that interval, the supreme of my function inside that interval, I have the following bound for it. This bound depends on the length, that parameter L I chose, as well as the L2 norm of the function and the L2 norm of its derivative. You can make this look a little bit nicer by bringing in a geometric mean. Whenever your L, so this condition L being less than or equal to the length of the interval is important. And whenever I can choose L optimally by picking the L2 norm of F divided by the L2 norm of the derivative of F. And assuming that is an acceptable parameter, meaning less than the length of the interval, we actually get the following bound. We get that this above inequality is bounded by the geometric mean of those two summands, right? So let's, prove the lemma. So this is actually, this is going to be basic calculus. Our starting point is the identity that f of t is equal to f of, f of t minus f of s is just the integral of the derivative, right? I think I want to use the notation I used in the notes. Okay, that's pretty easy to do. And so we can, that's the, what is that, mean value theorem from calculus, something like that. So in other words, we have f of t is equal to f of s plus the integral of the derivative. And this is whenever, so I'm assuming now t is in I, and I'm also assuming s is in I. Because I've only told you my function lives on I. Right. So now if I just take absolute values, that's less than or equal to this. Great. And I can apply the triangle inequality so that I can move the absolute value inside there. And the cute trick now is actually I average over all the s inside of I prime. Where I prime is an interval of length L, which remember is less than or equal to the length of I. So I can actually find such an interval. And when you average over these, well, that just means that this is going to be less than or equal to 1 over the absolute value of the length of I prime. And then I do the averaging on this end too. Oh, yeah, I do that by, sorry, I could have, I could extend this. So if T and S, I'd extend this to the interval I prime first. So as long as.
So this interval I prime is some interval containing T?
Yeah. That's what I was just about to say. Thank you, Rob. So I prime is going to be mainly chosen to contain T. And then we average over all the remaining S inside of I prime. Okay. It's I prime is any interval that contains T of the prescribed length L. But yes. Okay, so now I've extended that. I have that integral. And yeah, now you just apply Cauchy-Schwarz, right? So that you find Cauchy-Schwarz inequality implies that f of t is at most, okay, sorry, I didn't go through it. I meant to say there's an integral here over I prime. So I'll write this down properly. 1 over I prime, the integral over I prime of f of s ds plus, it's going to be 1 over I prime, the integral over I prime, the integral over I prime, the partial of f u du. Of course, these two just give you 1. And so now applying the Cauchy-Schwarz inequality, I actually get that 1 over I prime, the integral of, what is this? I prime with f of s squared ds to the 1/2, but also times the integral where I've got a 1 squared I prime to the 1/2 plus the integral, the same thing essentially, but with the derivative squared now. And then this thing right here, oops, this integral right here is just the length of I prime to the square root. So when you just collect the powers of I prime, or of the length of I prime, and you've got what you want, right? So this is equal to 1 over L to 1/2 that's supposed to be a U, I'm sorry. But I have these I primes here instead of the I's. But I prime is a subinterval of I, so I can just extend it. And at the cost of making this an inequality. We already had inequalities to begin with. Now this was for every point t, and therefore it's true for the supremum over all t. Great, that is a good point to stop. Were there any questions or additional comments? All right, let's end there then.